Today's essential question asks, how do we calculate the height and range of a projectile? I have a projectile launcher here, which I will use to send a marble into the air. We're going to choose to launch at this arbitrary angle. It is 26 degrees. Give ourselves some numbers here. So let's calculate both the height and the range of a projectile that is launched 26 degrees above horizontal. So I asked one of the students that's in class to please look into your journal and tell me what is the velocity that we can launch, the fastest velocity that we can achieve with this launcher. So we've measured previously the speeds that the launcher can, send at different sort of settings there. I think it's like 8 something, 8.18, 8.18 meters per second. So that's what we're about to see right now. We're going to launch a marble at 8.18 meters per second, 26 degrees above horizontal. Before we do, let's try to sort of get a prediction here. How far away will it land? We call it the range. And it's equal to the x component of velocity. We'll have to resolve this vector into x and y components. So it's the product of dx, the x component velocity, and the time airborne. Okay. So the total time airborne times the x component velocity gives the range. Now the height, the maximum height, right? So it's going to sort of get launched, it will at some point reach maximum height, and that's the point that we want to sort of solve for right there. So the first thing that we consider is resolving the vector as I mentioned. So we're going to break this down into its x and y components for ourselves. Here. There. So the initial y component is the sine of the angle times the velocity. So in your calculator, you can evaluate the sine of 26 times 8.18. I'll calculate it. We got ourselves 3.6 meters per second up. And so that's the up speed, about 3.58. And so the x component will be cosine of the angle 26 degrees times 8.18 meters per second. So the x component is going to be cosine of 26 times 8.18 to give us 7.4 meters per second. That's the x component of velocity. So that will substitute in here once we calculate what the time airborne is. How are we going to get the time airborne? We consider this point here where we recognize that gravity has slowed the y component of velocity down to 0 meters per second. So only thinking about the y component now. We know the initial velocity is 3.6. We know the final velocity at this point is 0. And we know that the acceleration due to gravity is equal to negative 9.81 meters per second squared. Let's get in the habit of using 9.81 for gravity. So that's 3 three givens, three sort of known pieces of information, so we can use our equations of motion to solve for a fourth unknown. We could solve for the displacement, and then we know the height, because that's also where we're interested in calculating the height. Let's solve for the time first, though, so we can finish off this calculation. And sort of knowing the time here, that'll be even more helpful in solving this one. So the equation that we use to solve for the time, the max height, is colors here. V equals U plus AT. Okay, so equation one, that just really is the definition of acceleration. Change the velocity over time. We can rewrite it to make the final velocity of the subject. Here we want to really solve for time. So we're really thinking about if something starts out at a speed of 3.6, this term AT has to be the negative of this, right? So we're saying how long t, this negative 9.81 meters per second squared of gravity, has to act on this object that's initially going this fast until it slows down to zero. So remember, this term is negative because the acceleration vector is negative relative to upward being positive. This is a positive upward speed. And so computationally, let's just look at sort of what this becomes. We subtract the initial speed from both sides. And then we divide both sides by the acceleration due to gravity. So times goes positive again, we're dividing two negative numbers. And so you can just kind of think about this computationally. Anytime I'm doing calculations like this, I'm essentially taking the initial speed and dividing it by gravity to get the time concept. Right? Like that's what this becomes. It is that because we're plugging in values into this equation and we derive this equation, you know, it's a good one for constant acceleration. Gravity is a constant accelerator. But if you just sort of think about it, you know, purely computationally, the initial velocity divided by gravity solves for the time concept. And this sort of shows why that works. So we take our 3.6 divided by 9.81, and we can deduce something that we really wouldn't be able to measure. It'd be hard to push a stopwatch and measure the fact that it will take 0.3, let's just say 0.37 seconds to reach max height. Okay, so this is the time that you calculate, again, with this initial velocity reaching a temporary final speed of zero, right? Like gravity's going to speed it back up in the downward direction. Assuming symmetry of motion, the time airborne is just going to be twice the time of max height. So if it takes, you know, 0.37 seconds to go up, it's going to take another 0.37 seconds to go down. Solve for this. Total time airborne over here is going to be 0.3. I'm going to do it for exactly 0.37 times 2, 0.74 seconds. So we have all the ingredients now to calculate the range, right? The x component of velocity, 7.4 meters per second, times 0.74 seconds. Hey, how about that? 7.4, 0.74? It just worked out that way. We can now conclude that every range problem will always be like that. The numbers will be the same. No, it's not a good extrapolation. That's a coincidence for this problem. So it should land 5 points. Let's just say 5.5 meters away. We might start to get a little uncertainty here because we're really going to watch this, right? We want to sort of see that the land 5.5 meters away. How high up will it go? One way to calculate the height, the maximum height, is to consider, like, what if we just had an object here and we let it fall to the ground? How long would it take that object to fall? Well, take it 0.37 seconds, right? Because just like we said, it took 0.37 seconds to go up. It takes that far to go down, whether we drop it from here or let it go along this trajectory. Gravity doesn't care if you're moving sideways. It brings things down to Earth at the same rate. So if we consider an object that fell from here, we know how to relate the time it takes something to fall in our gravity field to its height. Okay, so that comes from the equation of motion. S equals ut plus 1/2 at squared. So this is one of our equations of motion. We see this part right here is the range equation. Range equals vxt, right? So if there's no acceleration, then you just have sort of the range, the distance, the displacement is equal to the velocity times the time, because the acceleration is 0, that term is 0 in the x direction. So you just get sort of non-accelerated motion. Remember that the learning objective is students of physics being able to explain projectile motion in terms of the non-accelerated motion occurring in the x direction and the accelerated motion occurring in the y direction, the vertical direction, the gravity axis. And that's kind of like where this term becomes important. So the equation is always valid. It's just, well, in the x direction, a is 0. So that term goes away. But in the y direction, that's negative 9.81, right? So it doesn't go away. But if we assume we're dropping something from this point, dropping means 0 initial velocity, right? So we can kind of just say, well, we've got the equation of the displacement in the y direction is equal to 1/2 the acceleration due to gravity times the time to fall squared. The displacement in the y direction, we can call the height, h. And so this was kind of like the shortcut equation that we based our drop lab on. The drop lab, we related the height of a falling marble to the time that it would take to fall. And that's related by this equation. So that's a nice equation to use now to calculate the height. We can just say something that falls for 0.37 seconds, square that, that's t squared, times it by 9.81, times it by 1/2, and that's all for the height. And so that's how we calculate the height of a projectile. That's one of the ways to do it. Remember, as we mentioned yesterday, many paths to the same correct solution. You have different equations of motion that are valid here. This is just one of the ones that we could use to solve for displacement. So 1/2 of 9.81 will always be 4.905. So you could say an even shorter shortcut equation is h equals 4.905 t squared if it's Earth, right? Like that's t on Earth. 4.905 times 0.37 squared equals, anybody have it? 0.67 meters. All right, so we have some predictions. If I launch a marble at 26 degrees above horizontal at 8.18 meters per second, the marble should go a maximum height of 67 centimeters. And it should land 5.5 meters away. How far downrange do we need to go to observe the height of 67 centimeters? Like, when will it be this height? What number? How far downrange do we have to go? Here's the nice thing about this range calculation equation. You can plug in any time and solve for the range. I could solve the range 1 second after its motion. Well, 1 second after its motion is already down. But I can say 0.1 seconds after its motion, 0.2 seconds, 0.3, 0.4, 0.5, 0.6, 0.74 seconds after its motion. I can solve for the range. I know it's only going to be airborne for that long, so it doesn't make sense to calculate after them. But I could say, hey, 0.37 seconds after its motion, what's its range then? And this is actually one of the ways to calculate range. You could always calculate like the half range. Remember, we doubled the time to get the total time airborne, but we could have said, well, what's the range up to this point? And then we have the answer to the question I just posed. How far downrange until we are at that max height? So the symmetry of motion says, once we go half the range, we're going to be at max height, then it's going to fall down sort of the rest of the way. So at 2.25 meters, that's where I should observe it's reached maximum height. And furthermore, that maximum height is quantified as 67 centimeters. So we've got some predictions here. Let's go on a ruler walk around the lab. 1, 2 rulers. These are meter rules we're selecting now. That's the demonstration of gravity, still working well. And plenty of rulers here. Let's get ourselves be like this now. see downrange. You can see I've got a marble launcher with a 26-degree angle. Ready to go right here. Now we aren't accounting for the fact that we're 19 centimeters above the lab bench. I really should launch it at the level of the lab bench. I shouldn't let it just sit on the table. We didn't account for that. So I think I will have to adjust that. That's 2 meters away. This is the 3rd meter rule that I'm placing down. So this would be a range of 3 meters. So 2.25 meters right here is where we're expecting there to be maximum height. So as I launch, the camera goes. So once the marble is going to kind of come from this part of the screen this way, once it gets here, it should be crossing at this height right here. Okay, so this is how high it should be going. So if you look at kind of the way the camera is, see the bottom of that piece of paper on the wall over there? That's about where it should pass. Okay, and again, we're not accounting for the wind and the uncertainties of the apparatus, so it's a rough calculation, but that's the prediction right there. We got there for now. Let's get our entire range. So we're 3 meters downrange. Now we're 4 meters downrange to this point. 5 meters downrange to here. 6 meters and 7 and change. But we should expect to land 1, 2, 3, 4, 5.5 meters away, right about there. Okay, so just sort of work right here. The 2 lab benches sort of separate. You can't see that anymore. So somewhere around here is the prediction. Again, there's some uncertainty. All right, so 67 centimeters is right here. Okay, so it's like this, like a few centimeters above this. This top one is at 63, so it's a few centimeters sort of above that. So that's kind of, you have to get eyes on the marble as it's launched. We're looking for this spot, this far downrange is what we calculated. On Friday, we will explore this idea further and play a little game with it where you all can calculate how far away you expect the marble to land and see if your hypothesis is correct. We'll test a whole bunch of different hypotheses and like I said, we'll sort of get a game out of it. The rules of which we crafted over the years. All right. So we will now launch in 3, 2, 1. So it definitely didn't land as far away as we calculated. That's okay, right? So okay, we'll land other things to affect that. Probably uncertainty in the firing apparatus more than anything. But then here it seems like it actually went higher, which again you might expect because, as I said, I was going to move that thing down to the level of the weapon, but I didn't do that. So we actually need to run it again. Can you see that one? All right. Try it again. This time Move it. Level with the left. Try it again. Here we go. 3, 1. Perfect strike. But it wasn't a perfect strike at 60 or 200, like here about 50. So well short of the calculated height. Try that again. Make sure it wasn't fluke. Also, I'll try to get it past the ruler there. At least if we get the range better, we get the height. Three, 2, 1. So I think that actually was pretty close to the height. Still short on the range. And the marble still has energy even when it lands. So think about how we're only accounting for how far away it's going to land once gravity's done, sort of accelerating back downward. That's not to say it doesn't still have energy when it lands, and it's still going to be an object, in motion. I want to remain in motion until the outside forces of friction, kind of slow it down. We're interested in the question, how can we calculate the height and the range of a projectile? View, it's like I can see this color chop pretty good, the blue not so much. So the height is calculated by using an equation of motion like this: h equals 1/2 gt squared, where once we know the time that it would take an object to fall, plug in 9.81 for gravity if we're here on Earth, and you can solve for the height using that equation. We practiced with the range before. It's the x component of velocity times the time, and the time has to be calculated again by considering how gravity is an accelerator in that direction. So you can't avoid with projectiles the fact that there's accelerated motion in the y direction. So we apply the equations of constant acceleration in that direction, but there's non-accelerated motion in the x direction. And the combination of those two things is the parabolic trajectory that we associate with projectile motion. Thank you for watching, and see you next time.